Hi everyone, this is Rainita, and today we're going to be covering Module 6, Asynchronous Learning, STATA exercises, and we're going to be covering matching, different kinds of matching in this example. And if you haven't already, I would definitely look over the lecture slides as well as the Asynchronous Learning packet. And we're also going to be covering material from Scott Cunningham's Causal Inference mixtape. We'll actually be getting these examples directly from there. And so if you want more context, definitely feel free to check out the chapter on matching. Also, you should check out this paper that we're going to be recreating some of the estimates from if you have time. We're not going to necessarily be going through table by table like we have in our other sessions together, but rather we're going to learn more about how they apply matching. And I will give you guys a fair warning ahead of time that we're not going to get the exact same numbers as this data does, because the data that we're going to be using doesn't contain the full set and is not the exact same values. So they will be slightly off, but they will still be the same sign and similar magnitude. So to start off, let me just give you guys some motivation on this paper if you guys haven't read it or not. But this paper is looking at the effects of non-experimental studies. So reevaluating the evaluation training program. So there was this national supported work demonstration. It was a labor training program and for post-intervention earnings. So they basically have this randomized evaluation and randomized program of treatment, which is training. And it's given to one group of people by random, and another group of people are controls. They don't get this. And later on, they look at the earnings of the people that did get the treatment versus the ones that didn't get that training treatment. And they find that initially, what's found is that the training actually has a positive impact on earnings. So the people who were trained ended up having more earnings compared to the control group. But initially there was this paper in 1986 that Lalonde wrote where they wanted to address how comparable experimental data was with observational data. And so they have CPS and PSID data, and they want to see if we can find the same results. If they take a randomized experiments and they kind of randomize the data that they collect during that same time period and run similar analysis, are they going to find those same results? And what they find is that the randomized evaluation of the program when you use observational data does not hold when you're using the observational data rather than randomized experiment. And so the training does not have, a positive impact on people's earnings. But, one main problem with this study that is later investigated by these authors, Dehejia and Wahba, in 1999 in this paper that you guys have in Canvas, is that the data used by Lalonde doesn't have a balanced covariates, meaning that the control variables such as age, maybe race, sex, those kinds of variables were not balanced in the treatment and control group. And if you don't have a balance, meaning, similar number of people in each of those groups, if your treatment and control group are very different, like let's say we're comparing 20-year-olds who get this treatment to all the controls being 40 or 50-year-olds, well then, you may get a difference in earnings, but that difference in earnings may have nothing to do with the treatment that you assigned. It could be due to other factors such as age. And so the issue with the study that's later investigated is how can we better create, a treatment and control group that's comparable on observables. That way, it's kind of recreating a randomized experiment, because the intuition between randomization and experiments is that if you randomize who gets and doesn't get the treatment, then you're not creating any bias towards a certain group, and so your results shouldn't be biased because there's no selection bias. You're not selecting one group over the other, So you're truly trying to get the, true causal effect. And so that's what the study does, is they use propensity score matching to deal with the problem that there is a lack of comparability between the two groups initially if you just choose random data from CPS and PSID. And so that's the gist of it, but now we're going to go into some of the code for this. And I'm actually going to be taking a lot from Scott Cunningham's website, as well as his own functions that he has. So, STATA has some built-in data sets, and usually you can, put in the use function to be able to get those data sets. But we're actually going to be creating a program that's called SCUse, so Scott Cunningham use. And this code is in the do file that you guys have on Canvas. So, I'm not going to type this out line by line because I just copied it from his website as well. And by running this program, basically we're going to have access to all of the data we need for this example, as well as some of the functions that we need to run the density plots. And so we're going to just go ahead and start off. So we're going to just run this program, and you guys don't need to know this code for exams or anything like that. This is just being able to create a program to use this SCUse function later on. And that's what's important, is being able to use the SCUse. And its goal is just to be able to load in data sets. So now that we've downloaded this SCUse, let's go ahead and use the function, test it out, see if it works. And it's going to be called training example. So we're going to run that. So now we loaded in a training example, and this first one is just going to give us a good example of why we need matching. So this one is actually not coming directly from this paper, but it's a very similar idea. We have a treated group, we have an untreated group, our control, and then we have the age of the treated and the age of the control. And the reason why we're starting at this level of an example is we only have one covariate that needs to be similar or balanced between the treatment and control. And in this example, Scott Cunningham has already created matched samples for us. So we're just going to look at, when you have a data set, how do you even determine you have a covariate imbalance? How does one even go about checking that? So let's go to the data browser and see what everything looks like. So you have a unit of treatment, and we have the age for treat, and then you have the earnings for treat. So you can see that this is all red. We're going to have to fix that later in our code. I was going to fix this for you guys and upload it, but I think it's important for you guys to know how to, fix the code, even though it's tedious. It's going to help you guys in your homework to know how to manually do this. And when it's red like this, and then we have our control unit. So these are all of our treated units, and these are all of our controls. So we could imagine that these ones got the training versus these ones didn't get training. These are the age for the treated, age for control. So the first thing we can notice is that there's many more control than there is treatment. And that's actually good. You would expect that they should be balanced, but in reality, if we're going to use matching, we want there to be more control units, which is called our support. That's what the control is called in matching. And that way, there's more likelihood chances that we can find an exact match to the treat. So, for example, you have unit treat, unit control. You have age treat. We have 18. Let's see if we can find an 18 anywhere here. Okay, we have an 18 right there, and that's the only one that I can see right now. When we're matching, what we're going to basically be doing is taking the earnings for the control when they're at the same age as the treated and make that our, earnings for the matched. So instead of us pairing, just one by one, when the age is off by 2 years, let's match 1 by number 14 because the age is the same. That helps us kind of control some other factors that could be impacting earnings. If we compare an 18-year-old by a 20-year-old, you can think back, there's, maybe a stark difference. This is beginning college to almost finishing or being midway through. more job experience that one would get as a 20-year-old. So it's not very comparable. So then if we look here, our unit matched, we have 18, right? Which is 18 years old. And their earnings matched is 80/50 because the control was 80/50. So basically now we can compare this with this. Same thing for 29. So let's see, 29-year-old. Let's go to age of the control. Is any of them 29? There's a 29 right there. That's the only one I see. So we can use 105 or 10,525 as the matched. And so that's going to be the earnings there. And so on and so forth. So let's say we have 24. And we don't have a 24 here. We do have a 24. I take that back. It's 9,400. So that's going to be our matched. And then 27. We do have a 27. Just one of them. Let's see if there's an example where they have doubles. So this one has doubles. 33. There's a 33 and then another 33. So what happens if you find two? Well, these actually end up being the same earnings, but what you would do is you would average these. You would add this one plus this one and divide it by 2. If there was 3 of the same, you would add all 3 and divide it by 3. So that's just something to note. And that would end up going here. And that's what they have. So that's how one does matching. And I just mentioned how we had something in red, and it's going to give us an error that I'm going to show you guys how we can fix that. So we took a look at the data. Now let's look at a histogram. That's helpful as well to see what does the age of the treated sample look like. We can bin it by 10 and look at the frequency. So basically the dispersion of our age is we have a lot of people in the treated group that are within the 20 to 25 range, some in the 30 range. And let's say we want to compare that with the histogram of age control. So this is our one observable covariate of interest here that we want to be similar between both treated and control. And what do we see here? We see it's very different, right? So now we see a lot of dispersion in the age. We see, a high frequency at 40 as well as 50, whereas before it was all centrally from 20 to 30. And so we can definitely see a stark difference in the histogram in the age for treated and control. So let's look at the summary statistics of the variables of interest to compare the means now that we've looked at the graphs. So if we do sum age treat age control. So if we run that, first we can observe that the observations, there's 11 here and 21 there. And there's, a pretty, vast difference here. There's about a 7-year difference in the average. And so we don't really want to be comparing treatment on two groups like this, because there's another observable, covariate that could be driving the differences in earnings in one way or the other. And so let's try taking the sum of earnings tree and earnings control. So you don't see an error message here, but you see earnings tree is listed as 0 observations. But when we saw the data browser, we know that earnings tree does have observations, but they're in red, and that's because there has been a manually added character string in this column, which makes STATA unable to really comprehend whether this is a numeric or string. And so because of that, let's just recreate that earnings column. And I want to show you how we would do this manually. So let's just drop the earnings tree column, and now let's gen earnings tree equal to 9500, which is the first one. If you guys want, you can first tab earnings tree so you know what the different ones are. So you can also sum it as well if that's helpful. That's not helpful, it gives us 0. So let's say gen earnings tree equals 9500 if unit tree equals 1. Double equals. So what does this mean? It means if unit tree is equal to 1, that means our earning tree should be equal to 9500. And we're going to do the same thing for all of these. If unit tree is equal to 2, earnings tree is 12,250. So let's do that. Replace earnings tree equals 12,250 if unit tree equals 2. Replace earnings tree equals 1100 if unit tree equals 3, and so on and so forth. This is good to get some practice because sometimes in our homework we are going to have to manually do this. Usually we can run a for loop or something to make the process simple, but if it's something like this that's based on placement of another variable, condition on another variable, it's also good to know how to simply just create a new variable based on unit tree. Okay, so now we're done. Let's make sure that this runs okay. Okay, all of that worked great, so we can check it out now. Okay, we have everything we wanted here. So that's our earnings tree. And we can reorder the variables so that they were kind of in the same place that they were before. Unit tree, age tree, earnings tree. So all we did here is just put everything back in order, and now it's not red anymore because there's no characters with the string. Sorry, characters with the numeric. And now we can actually run our sum command, and it'll actually make sense for us. So let's go ahead and do that. And now we have 10 observations, and we can see the means are quite different. So we have 11,101. Actually, I take that back. The means are very similar. It's the standard deviations that are a little bit different now. So out of these 10 people and these 21 people, the averages are pretty similar. They're just, $30 here and there off, but the standard deviation from person to person is, very different. The control group has a much larger standard deviation, meaning there could be some people that are making lots of money while others are less, and that's why the average is here, while the standard deviation is smaller in comparison for the treatment group. So that means that people are on average, at least compared to the control group, earning about that average 11,075. So that's one difference that we see. And this is what we would consider our simple difference of means if we just subtracted the two. And now let's go ahead and take the histogram of our age tree and let's compare that to our matched histogram. So here is our treatment, and our match histogram looks like this. So they're very, very similar. Let's go ahead and look at that again. It's very, very similar. They are almost the exact same. So we've done a good job. They are the exact same. We've done a good job with matching because luckily in this sample, we were able to find a matching age for every treated unit in the control unit. And so now the only difference is their earnings. We're not comparing it based on many observables, just the earnings, which is our actual dependent variable of interest. And remember, how do they get the match sample? All you do is start with your treatment, look at the control that you're trying to match on, and try to find that in your control covariate column. Once you find that, take the outcome, and that becomes your matched outcome. Then do that for the next value of age, 29. Look for 29, and that becomes your outcome. And so these are your matched sample compared to the treated sample. Okay. So this is also considered nearest neighbor matching. And nearest neighbor matching typically is looking for the closest neighbor to the treatment. It's also, in this case, exact matching because we actually found an exact equivalent to the treatment. So the distance between the treated unit age and the control is 0 because we're finding the exact same. Suppose there was an 18 here and there was no 18 here, but there was only a 19, like this one, then the distance would be equal to 1. If we're looking at Euclidean distance, there's also different distances that you can look at, such as, I'm going to say this incorrectly, to the histograms. Let's go ahead and look at the summary command for the earnings matched and the earnings tree. And so this match group is going to be considered our control group in a sense, in which we're going to compare where our age is matched to the treatment that didn't get treatment on earnings effect. So if we just compare these means, this is our simple difference of means or average treatment effect in this case. And we can do this by displaying 11,750 minus 9380. And we find that our treatment effect, or SDO, is $1,695. So what that means is that being in this training program, being in the treated group, increased earnings by $1,695 compared to those that were not in the training group. And we also know that conditioning on age, by matching our age, we are able to tell that this is a truer causal effect of the training, and there's not other observational data that could be skewing or biasing the results. The average treatment effect, and we've seen the impact of matching in a simple scenario where the data is already matched and we're using exact matching. Let's go ahead and move on to our paper here. And we're going to be looking at the causal effects in non-experimental studies. And I'm also going to keep the mixtape open here for us to compare results that they get. And let's just go ahead and start with loading in the data. So I recommend you copy and paste this from the do file if you're following along, because it's really easy to get the website name wrong. And if you notice, it has a comma clear at the end, so it's going to clear out our previous data set. And this is just the GitHub link for Scott Cunningham's mixtape data. He also has in the book SCU's and SW data, but that doesn't work for some reason, so we're just not going to use that. And now we'll just go ahead and take a look at what our data looks like. So we can first visually inspect it like we've been doing. So we have our data ID from the Dehejia and Wahba sample, so that's from this paper here. And then we also have our treatment, our age, education, all these other covariates, and we have earnings for 1974, 1975, 1978. So let's take a look specifically at one of the main results, is the earnings in 1978. And you can just put if tree. If you put if tree, it's automatically gonna show you if tree is equal to 1. If you want, you can also just put equals to 1 for consistency, but it gives you the same results if you just put if tree. So we can actually generate a variable based on this treatment, showing that the average for people who got training for earnings in 1978 was 6,349. Let's store that result by generating y1, that can be our treated group, and let's make it equal to the mean. So this R, you can think of it as return. It's going to return the mean of what we just ran. So it's going to create a column that is equal to 6,349. Now we can try doing the same thing for the control group. So sum, you can also put STA if you want. STATA recognizes the same thing. If tree is equal to 0. And that's 4,554. So it does show, if we're just looking at it in a naive comparing means way, that the treated group did do better in earnings, but we're going to investigate more using matching. So then we can create this mean. Let's go ahead and run that. And yeah, that's the same thing, 4,554. And now we can just generate an average treatment effect variable, which is equal to y1 minus y0. And that's going to be equal to 1,794. So that means our simple difference of means, or average treatment effect, it's the same in this case, is equal to, you can also sum ATE to get that number back. It's equal to 1,794. And now that we've taken a look at what the average treatment effect is, let's actually go ahead and start using some of the matching techniques that they use. So we're going to have to load in the CPS data for this, because they want to look at how observational data can be used as a control group. And we're going to have to match unobservable covariates here as well. So first, let's go ahead and just drop our variables that we just created so that they don't create any confusion. And then we can compress the data, which just changes it from a float to a byte, which is a different type of data. So now they're still numerics. And let's drop if tree equals 0, because the whole point of loading in the CPS data is to create our control group from our observational data. So we don't want to use experimental data anymore, because we're going to be using matching with the observational data. And I again really suggest to just copy and paste this line, because it's really easy to get this website wrong. That'll throw everything off. So we're going to append the data, which is a little bit different from merging it, in the sense that it's just going to stack the data one on top of the other. So we can take a look at what that looks like. So instead of merging left to right, it's up and down. So we have our original Dehejia and Wahba sample, but if we keep going down, now our data ID looks like CPS at the bottom. So our treated group is coming all from Dehejia and Wahba, and then we have a really big common support, meaning control group, to create matching from with our CPS data. And none of them are treated, right? Because they're not a part of this experiment. They're just survey data that we're using to compare and contrast. And now that we've appended this data, we can take a look at some of the some of the different regressions that they ran in the table of this paper. So here they're just comparing the data and looking at the observations and the differences of means. This is really important when you're running a paper, is you just want to lay out a descriptive stats table that compares the means and the amount of observations you have. So we can see that there's actually a lot of differences. The PSID comparison groups are, older on average compared to these ones. And that's table 2. Let's go ahead and step down to table 4. So this is a sample means of characteristics from matched control samples. So let's go ahead and see if we can create some matches now. So the first thing we're going to want to do is we're going to want to run like a logit regression to predict the PS score. And in order to do that, let's go ahead and create the different covariates that they use in their specifications. And so they're creating control groups by squaring and cubing some of the covariates that we have. So let's go ahead and start by generating an h squared variable, and this is something that we discussed in Econometrics 1, why we would need to do that. It could be the case that, we have diminishing marginal returns or whatever the metric is over age. So that could be a reason why we need to square it or cube it, because that's maybe a better fit. And we're going to use this ren option, and ren just means rename. So we're going to rename education to school because that's consistent with the code that Scott has. And then we're going to generate school squared. It's equal to school squared. And then we're going to create an unemployment metric from our data. So if we look at our data, there's a bunch of zeros in the earning 74, earning 75. And so what we can infer is that if there's a 0 earnings here, that would mean that that person is unemployed at that time period. Whereas if there's a number, that means that person is employed because they're earning. And so we're going to use that composition to create our own unemployment metric. So let's first generate one for our earnings in 1975. Let's say it's equal to 0 if our earnings equals 0. Sorry, it's equal to 0 if our earnings doesn't equal a dot. And then let's replace U75. So unemployment equal to 1. So the person is unemployed if their earnings equals 0. And then let's go ahead and do the same thing for unemployment in 1974. So it's equal to 0 if earnings doesn't equal a dot. That means the person's employed, but it's going to be equal to 1. That means the person is unemployed if the earnings equals 0. Now let's create another dummy variable for the model. So they create one of RE, so earnings from 1974 squared. So then again, they're playing along the lines that we may not have a linear relationship. It may look like something else. So let's generate our first interaction, which is whether somebody went to school, got education, and their earnings. And then another one, let's do earnings of 1975 squared. So it's going to equal to RE75 squared. And then let's create an interaction. Our second one from the paper is U74. So whether you're unemployment and if you're Hispanic. So we can go ahead and run all of these. And it looks like I've spelt something wrong somewhere. Let's take a look. And it's right here. So let's see if we can rerun this code. Okay, all looks good. So now that we've created these variables that they've used in the paper, let's go ahead and estimate a propensity score using a logit model. We're going to stay consistent with the paper in that sense. So we're going to logit, treat, whether you were treated or not, age squared, age cubed, school squared, married. Just want to look at school for a second. Okay, so school is actually not a 0-1 indicator. It's the amount of years that you went to school. Married, no degree, Black, Hispanic, employment in 1975, unemployment in 1975, and the interaction that we just created. And let's run this. And we can use the predict command afterwards, and we can do predict PS score, so propensity score. Okay, so now that it's done that, it's created a propensity score. And we can take a look at this. What does that mean? It means the probability for treatment. So if we take a look at that here, it's saying that the propensity score of this person, so the probability of treatment is 0.33, 0.566, 0.02, so some people don't have a very high probability for treatment. So let's just kind of discuss what does a propensity score mean. So instead of exact matching, it's basically giving us a probability for an individual to be treated. And it's going to be based on the different covariates that we specify in our model. And basically it's saying, so first thing is we want to be able to satisfy our CIA, right? Our conditional independence assumption. And so the idea is that condition on some variable X, so in this case our observables like age, or what else do we have? Years of school and such. We are able to find independence. So basically our samples should be random and independent from one another. And so the propensity score is basically saying that the probability of being treated based on these other characteristics and comparing that to the characteristics of the treatment group, this is the probability that one would be treated. And it's looking at the entire treatment group's characteristics when it's creating this propensity score. It's taking a maximum likelihood. And Scott actually does a really good job at explaining this, what exactly is happening. And if I can find it, then I'll kind of just read that sentence that does a really good job explaining what's going on here. So basically, propensity score matching takes those covariates needed to satisfy CIA, estimates a maximum likelihood model of conditional probability of treatment, and use the predicted values from that estimation to collapse those covariates into a single scalar. And if conditional on X, two units have the same probability of being treated, then we say they have similar propensity scores. If two units have the same propensity score, but one is a treatment group and the other is not, and the conditional independence assumption credibly holds in the data, then differences between their observed outcomes are attributable to treatment. So what that means is that if they both have the same probability or likelihood of being treated, and one is treated and the other is not, and this conditional independence assumption is met, then we can actually estimate the differences between the outcome variable, so for this case earnings, and we can actually attribute that to the causal effect of treatment, which makes sense, because if this person had the same likelihood as somebody else that has the same likelihood, I guess these two are better examples, these two people have the same likelihood of treatment, but one was treated and one was not, then we could actually just subtract out their earnings, because we know that they're not different on other observable characteristics that would change their likelihood of treatment. And another thing, maybe not discussed so much in the paper, but discussed in the textbook, is the curse of dimensionality, which is basically the idea that the more and more control variables that you are going to be using to match, you're going to have a curse of dimensionality, because the more and more sample that you'll need, because the dimensions will grow and grow as you have more covariates. So you're going to need a really, really big support group, common support. Not a support group, but really big common support from your controls to be able to find the accurate match on so many different dimensions, like age and gender and school. So you get this curse of dimensionality rolling up on you, the more and more covariates you would like to match on. And then with that specificity, you basically lose the ability to match on especially discrete continuous data as opposed to categorical data. And later on today, we will discuss when you have super specific continuous data and it's impossible to match, what you can do in that scenario. But let's just go ahead and continue along with this example. So we've created the propensity score. Let's now look at the mean propensity score for treatment and control groups. So we're going to sum p-score if treat equals 1. And I actually want to get the percentiles. So let's put comma detail. If treat equals 0, comma detail. Let's go ahead and look at those. So we can actually compare this to this Scott Cunningham's table where he has these as well. So he does the same thing here. So let me just go ahead and close this. We get 0.001, 0.005. So remember, these are not going to be exactly the same, but very similar. 0.002, 0.007. So we're in the ballpark, but not quite there. And that's just because of the way that this data is constructed versus the data, the original data from the paper and from the textbook. And then we get these percentiles as well. So now that we've looked at the propensity score, let's actually take a histogram so that we can compare the two propensity scores. Let's rescale the bins. And this is a good way to be able to side by side look at what they look like. So the probability of treat, graphs by treats. This is our CPS controls, and this is our actual treatment. So we see that the probability of treat is, pretty evenly-ish dispersed in terms of density. But in the control group, we have a very high probability to not treat, right? Because we have a high density at 0. And so in these, next models we're going to look at inverse probability weighting, and there's going to be an impact of the fact that this is density at 0 for that. So that's just something to note. But one thing that's really good is that we have a lot of control to match with. So that's going to help us a lot at correctly matching. So another thing that one can note here is that when you have a high density and 0 probability, basically that means that the characteristics of individuals in the treatment group are rare in the CPS sample. So such as age or maybe years of school. So that means there's a negative selection into treatment, meaning that we're not going to see a high probability of somebody being similar to the ones in the treatment group like a very close propensity score if the characteristics are very different. So if the individuals have these stark differences on control characteristics, then there will be varying distributions of propensity scores by treatment status. So that's actually what it means if we're looking at it in terms of our controls. And so now let's go ahead and use a different command. It's called TE effects. So we can first just look up help TE effects so we know why we use it. So it's treatment effects estimation for observational data. So you can use different kinds here. You can use augmented inverse probability weighting, which is what we're going to use. We're also going to use nearest neighbor matching and propensity score matching. These are all discussed in your textbooks. So nearest neighbor matching is in terms of distance. Propensity score matching is in terms of what we just created, the propensity scores, the probability to treat based on the covariates, and the inverse probability weighting is another method we're going to be looking at. And so let's first rescale our data. When we use TE effects, we don't want things to be in the thousands. We're going to want to scale it down a lot. So we're going to divide all of our earnings for 1978 by 10,000. And we'll just remember when we're interpreting results, we have to multiply by 10,000 because we had scaled. And now I want to go over something that Scott Cunningham does. He does this cap command, which is capture and return code. So capture executes commands suppressing all of its output, including error messages, and issues a return code of 0. The actual return code generated by command is stored in the built-in scaler. Capture can be combined with these brackets. So the idea is that you're not actually looking at the results. You're just capturing the results. And so for this first part, we can do cap and TE effects, where this N goes with it. Inverse probability weighting, re78 scaled, what we just created. And we're going to use treat, age squared, age cube, education squared, married, no degree, Black, Hispanic, or earnings from 1974, earnings from 1975, employment from 74, unemployment for 75, the first interaction that we made. We're going to use a logit, close that up, and now we have to have this O sample. So these are all the syntax for this TEFX IPW, inverse probability weighting. So first we want our outcome variable. So this is our outcome. We're looking at earnings from 1978. Then we want to specify what is our treatment. So it should be 0, 1 indicator of people who got treated and not treated. And then we want to specify all the different covariates that we're interested in that we would, potentially want or test to be similar to one another in the control and the treatment group to have comparable groups, and what we would run in our logit regression as well. And then it requires us to make this overlap sample, or this overlap variable, which basically is a variable that's going to show whether there's an overlap between the treatment and control. And we're going to delete later on when the overlap equals 0. That means there's no overlap in any of these covariates, and we're only going to use the ones that do have an overlap. So we can run that command, and education is not showing because remember we had named it school. That might happen to something else. Let's check. Okay, and so we get an error message here, but let's go ahead, and that's because the parentheses scores are less than this amount, which is very, very small. So, and there's a large amount of treatment that has that low propensity score. So let's just go ahead and carry on and see what happens. So let's say we keep if overlap equals 0. And we can also do help overlap to see exactly what it is. So estimates potential outcomes, average treatment effects, and average treatment effects on treated using observational data. Overlap plots the estimated densities of the probability of getting each treatment level. Okay, so let's drop overlap now, and let's run it again. So now we've kind of taken out all of these ones where overlap is not a 0. It looks like overlap is a 0 for all of them. Let's go ahead and see what it looks like now. Again, it's a logit. Same issue. It says variable overlap not found because we had already dropped the overlap. So let's go ahead and run this now. Okay, so now that we've only kept it if the overlap is equal to 0, we're actually getting real results here. So it's inverse probability weights. We use a logit, and so we get negative 0.601, which is pretty close to what they get in the textbook, but it's a little bit different based on the data. So we get our average treatment effect to be negative 0.601, and remember we have to multiply that by 10,000 because we had rescaled it. So we're actually going to get negative 6,000, right? And so the way we can look at this is that we're basically showing that there's a large negative treatment effect, and it's due to the inverse probability weighting, because the inverse probability weighting is causing the unit to blow up for very small values of propensity score. So remember, we had all those propensity scores that were really, really small. Like, it even gave us an error message. Your treated units have propensity scores less than, 1 times e to the negative 5th or something like that. So we're going to want to trim our propensity scores to see what kind of results we get once we kind of define our boundaries. So let's go ahead and trim our PS scores. So let's drop if our PS score is less than or equal to 0.1. And let's drop if our PS score is greater than or equal to 0.9. So now we're going to be looking at our average treatment effect in a range. So none of them were above 0.9, but we dropped a bunch that were below 0.1. So now let's look at the T effects of IPW, so inverse probability weighting. Okay, and we're also going to write here that we want average treatment effect on the treated. So let's specify that. And overlap already exists, so we didn't drop the overlap. the second time. Let's go ahead and do that. Okay, so now we actually find very different results, right? So once we trim everything, we get a positive coefficient. So when we're looking at propensity scores within that range, where basically the probability for being treated is bounded, it has to be greater than or equal to 0.1, less than or equal to 0.9. Then our average treated on the treated is 0.217, and remember we have to multiply that, so 174, we have to multiply that by 10,000, and so we can even just do so we have 21,740. No, that was too many zeros. So 2,174. So basically now we're finding that being treated, getting this training versus whether somebody who didn't get the training has a positive impact on earnings by 2,174. So that's good. That's a similar direction as what we saw in the initial study. So basically, when we use matching, we actually get more accurate results or replicable results compared to the experiment. And so this is differing from what Lalonde found. He found that basically observational data can't really be used when you're looking at experimental data to use comparisons, but this other paper that we looked at is saying otherwise. It's saying that, we can, once we use propensity score matching and find a comparable control group. So now we can finish our capture. We can capture and drop overlap. Nice. So now that we've done that, let's go ahead and try using a different technique. Instead of inverse probability weighting, let's use PS match, which is going to look at the nearest neighbor matching for propensity scores for a matching. And we're going to use a logit as well. And we're going to look at the average treated on average treatment effect on the treated units. So let's use the T effects again. PS match now instead of IPW. And the same format. We want our dependent variable, we want our treated differentiation, and then all of our specification from our logit. Average treatment untreated, and then we're going to actually generate a variable. This is going to be a propensity score, the CPS, and we're going to use nearest neighbor of 5. So basically this is the distance. So as long as you're within 5, so your age is within 5 years, or your other, education is within 5 years, you can be a score or a match. And so the larger we make that number, basically the more lenient we're being and what constitutes a match. You could play around with that number and make it a 3 or a 2 if you want an exact match, but it depends on how much control data you have. So here we get an average treatment effect. It's a little bit different from before. Before we'd gotten 2,174, now we get 1,858. And so we can take a look at this. So it's actually created a propensity score for the different characteristics. So it's figuring out how many different matches there are within the data. And we can now change it to, let's say we only want to do the nearest neighbor of 3 distances instead of 5. But this has already been created, so let's actually just create pstub instead of pstubs. And now we get an estimate that's really similar to what we had gotten prior. The average treatment effect on the treated. And so here we can see that when we actually create our nearest neighbors to be smaller, so it has to be within 3 values, then we're actually getting something similar to the inverse probability weighting treatment. And we can actually drop if our PS score is less than or equal to 0.5. So now we're just looking at the parentheses scores of 0.1 to 0.4 and see what effect that has on our average treatment effect. So now we're just looking at a very small bin. We're only looking at data whose PS score is less than or equal to 5. Okay, I see. So now we're actually looking at, sorry, I explained that wrong. I thought this was greater than or equal to. So now we're looking at PS scores that are 0.5 and above. So that means that the propensity of, or the probability of it being treated is pretty high. And we're looking at that for both the control and the treated group. So basically this person, based on their control their characteristics, has a 62% probability of being a treated unit based on all of the different treatment characteristics, and it was treated. Let's look at the controls. So this is really going to limit the amount of controls we have now, because we have basically required a very high amount of propensity score matching. So all of these people, based on their covariates, would have a high probability of being a treated unit. And so we're actually able to see treatment effect. So let's go ahead and see what is the average treatment effect when we have very high propensity scores. Let's check that out. Okay, so remember we have to times this by 10,000. So our average treatment effect, not on the treated, we didn't specify that, 0.392 times 10,000, so it's going to be 3,920. And so we're getting a really high average treatment effect. So when we make our treatment and controls very similar on covariates, so they both have a high propensity or high probability of treatment, we actually find a larger treatment effect. And so we could, conclude here that when our observables are very similar, right, we're drawing out the true causal effect. And it seems like when we're using this matching technique, we're able to find a high significant treatment effect here. This is 0.001. And so here we get that. And so we've tried our inverse probability weighting, we've tried nearest neighbor, Let's go ahead and try something different. This is a relatively new command and application. It's called CEM, so coarsened exact matching. So if you remember earlier, I explained how, I'm gonna butcher this, so let's see how we spell it. Coarsened exact matching. So remember how earlier I discussed how we could have continuous data that is just very similar. I'm sorry, not very similar, very different, because it's like, 132.56. And then having an exact match for that is going to be really difficult. And propensity score matching is also going to be really difficult because those are exact continuous numbers. And so when that's the case, we can actually do this kind of coarsened exact matching. And this is a technique that basically creates categories based on your continuous or discrete values. So instead of having, the person's 20, 21, 23, you could say, okay, there's an age group of 20 to 30-year-olds. Then there's an age group of 30 to 40-year-olds, or whatever you want the bins to be. And then you're able to actually find better matches because you can see in the treatment and control, there's similar people with those covariates or characteristics. So that's basically the essence of what this is doing. And this explains this probably better. Implements a coarsened exact matching. The main input for CEM are the variables to use and the cut points. So remember, these cut points are determining basically at what increments are you going to be creating your categories. So if you put a cut point of 10, 20, 30, it's going to do bin 0 to 10, 10 to 20, 20 to 30. So let's try this on the data and see what happens. You're going to have to first SSE install CEM unless you've already used it on your machine. I'm pretty sure I already have it, so I'm just going to comment this part out. And we can use CEM age, so that would be one of our variables, right, that is discrete right now, and maybe we'd want to create categories. So we could do 10, 20, 30, 40, 60, and you would want to like tab age to see what the cut points need to be. And so you see there's actually no one over 40, so you're fine because we've cut the data up so much that there's no one older than 40 at this point. And we would want to use our age squared, age cubed, so all the different covariates and variables that we created for our regression. And our treatment is treat, so the syntax is a little bit different. You put that at the end here instead of at the beginning. And I spelled something wrong. Okay, so I had cut up the data a lot, and that's why we're finding very little balance here. So we have after cutting the PS score by so much, we only had 35 controls whereas 67 treated. We were able to match 13, 16, and then unmatch for 22 and 51. So actually, I think what I want to do is I'm going to want to start off from before I had cut everything up. So let's see where that code is. So let's clear. Let's start off from where we were at in the beginning. Let's use that data and then drop if tree equals 0. And then let's append the CPS data. Let's start at this starting point. And then it'll give us a better run, right? Because we don't want to keep using one matching technique over another matching technique. It's not going to be able to show us what we want really well. Okay, age squared not found, so we're gonna have to actually create those real quick, but that's okay. We can just copy and paste it. So copy and paste your code from where you had created all these different covariates. Let's run that. Let's see if it runs okay now. It's running just fine because we see this loading bar here. It's just taking a second because now we've given it a lot of data to match by. Okay, so now we see a more full description. And so it gives us our age squared, the average for each of these variables, the min, the 25% quartile, and 75, and the max. And basically we had 15,992 controls, 185 treated. We matched 171 to 76 treated. And that's okay. That's how many were untreated. And let's go ahead, now that we've ran that, and figure out what our average treatment effect is using this method. So we do a regression with our dependent variable of earnings in 1978, and then we use our treat, whether you're treated or not. And it created the CEM weights here. So we're going to be using I weight equals CEM weight. And we're going to put comma robust or comma R. And so here it's showing our average treatment effect, and it's saying that it's $2,771. So it's very similar to what we had gotten prior when we were looking at our different inverse probability weighting techniques, as well as our nearest neighbor matching. So it is a lot larger though than what they found in their experimental effect. So remember when we were looking at the experimental effect of training, we found like it was like 1,695. So this is considerably larger, almost $1,000 more. And that's because instead of using our randomized trial, we're looking at control data from observational data that had nothing to do with the trial, and we're matching it on covariates, which technically in experimental data, you know, covariates should technically balance out or generalize because we're choosing at random, there's no bias. But since here we're methodologically choosing people similar on these other covariates, we may find not an inflated but a larger treatment effect than we would have in the experiment itself. So that's another way to do matching. So now we're gonna try a different function, and this is gonna be our last thing. I wanted to go over all of these things because it's in the book, and you know, it's not really explained a lot of times, so I just wanted to go over step by step what these different functions mean, because it can be a little bit off-putting when you look at it in the textbook. But there is actually, you know, a simpler way to run this based on a different function that I'm going to go over. And the benefit of this function is that it has a density plot that's able to tell how balanced your covariates are. So it's a really good kind of way to visualize your covariate balance. And so we're going to use the same data, but I actually uploaded a data set on Canvas that we used in our last year econometrics class. It's called the NSW PSID data. So I want you to set your working directory to wherever that data is located on your machine. And let's go ahead and load in that data. It's very similar to the NSW from this paper, but it's a little bit different. It doesn't show 1974. It's just going to look at 1975 and 1978. So let's go ahead and use a probit, which similar to Logit, but not the exact same. You can help probit if you want to read more about it. So our probit regression fits a probit model for a binary dependent variable, so similar to Logit when it's 0, 1. Assuming that the probability of a positive outcome is determined by the standard normal cumulative distribution, the CDF. Probit can compute robust and cluster robust standard errors and adjust results for complex survey design. So let's use a probit and let's look at whether you were treated or not. Age, Black, Hispanic, which I guess is the whole thing spelled out. Married, education, no degree. And employment for 1975. So we put QUI here. What that means is we're quietly running the probit. That means it's not going to report the outcome. If you don't want to look at your results window, if you do want to look at the outcome, you could just do it like this. But the reason why we're doing QUI is because we're actually not going to look at these results. Remember, you always want to run the margins command after you probit or logit in order to be able to tell what the true results are. So this is gonna look at the marginal effect based on the average of the other. Sorry, you can actually look at what this means. So help margin. So there's different specifications with margins. There's margins at means, which looks at the margins at the means of covariates. So basically you're looking at one variable and you're explaining it based on every other covariate being at their mean. Or you can estimate the margins at the specific values of covariates. So for this one, we used dy dx, so the derivative of underscore all. So estimates the semi-elasticity. So we're just basically, yeah, that's normal. So when we use a probit or logit, we're just looking at the semi-elasticity here. So we have that, and now we can predict. Double just means the type of variable. So we're going to predict the score, which is like the propensity score. But double just means that the variable that we're predicting, please store it as a numeric. And this is the score that we get. Similar to what we did before. But now we're going to use this density2 command for the score to be able to look at what does our data look like in a plot. So basically our propensity score, the probability of treated for ones that are treated, remember the density is pretty evenly distributed. We have actually a lot more that are closer to 1, which is what we would expect. So it's kind of a left-tailed, whereas here we have a right-tailed for the treated equal to 0. So that means it's the same thing that we saw earlier, that we have a high density at 0, which means that the characteristics in the control group is very different, is starkly different from the control characteristics in the treated group. And so that's gonna, give us a problem when we're matching. It's something we've already discovered before. Remember, this was a bar before, but now we've just laid one on top of the other. And I do want to note that this density2 function will not run on your laptop unless you actually ran this code up here. This has a special addo file, which goes in your laptop, in your program files for your computer, that basically downloads the density2 function. It's no longer in STATA. You can't just do ssc install density2. It won't work. What you could do is you could search density2. It's not there either. So let's see what happens if we go here. So ps match, ps test. So these are other different commands that it wants us to download. Another thing that you could do is you could go to Google and go to density2 addo, and you could go to GitHub. Not GitHub, this is GitHub. And you could download the density 2 here, this file, this is an ADDO file. If it's not letting you download, then you can copy and paste it into your, in here. This is not super important, but just in case you want to run that file, that density plot. If you use Scott Cunningham's program, the SCU's one, it should already download on your computer, but just in case, I just want to show you guys. You would basically save this. And the place that you would want to save this is, I already got to this. So you're going to want to go to wherever you have STATA on your computer. So STATA could be your documents, could be your applications. I have it in my downloads. So you're going to go to STATA and you're going to go to ADDO. You're going to go to plus, and it has all these alphabets that basically list off the different packages that we have. And so since we're doing density 2, we were going to want to put it here. And I already have the density 2 ADDO saved here, but if you don't, what you can do is just name this as density 2 ADDO, save it, and now it'll let you run the density 2 function. If none of this made sense, don't worry about it. This is not important for the class or anything. This is really important if you want to do matching and want to get a graph like the one that we just saw. If you need more help explaining how to get to where I got, we can just discuss it during office hours. Don't worry about it. But let's go ahead and also look at another graph. Let's actually export the graph that we just made. So we have it saved. We can export it as a PDF. And now we have it saved in our working directory here. And then we can use another function called psgraph. If none of these commands work and it gives you an error, you can just do ssc install. And our treated, it's saying what's the name of your treated variable? It's actually named treated. So we're going to put treated in there. And we're going to put pscore, we named it score here. And then we're going to bin it by 50. And we're going to save it as psm2b. Comma replace. You want to put the comma replace so that it's going to overwrite the graph each time you run it. So this one I spelt it wrong. Let's try that again. Okay, so basically what this is showing us is the propensity score for untreated and treated. So we again can see a very high density of 0 propensity score for the untreated units. This is very similar, this graph, to what we found in the density 2. It just is showing it in a different way. So you don't have to go through the hassle of getting the ADDO file if you like this graph better. We can also notice here that the treated sample, they have a higher density, closer to 1, than the control or untreated sample. And so this is kind of a good way to show that our propensity scores are basically saying that our treated group, our control group is very different in the characteristics from our treated group. So that's something to look at, and we can export that graph as well. That way it's saved for us to look at later. And now we can use this other function called psmatch2, which is going to use the propensity score matching. We can help psmatch2 to see what it does. Typed that wrong. Let's try it again. And basically it's just looking at Mahalanobis. I'm going to say this wrong. Okay, this propensity score matching, that's just a different distance. So there's this distance or there's Euclidean distance. So let's see if it explains it well. So it's basically saying it calculates approximate standard errors on the treatment effect, assuming independent observations. Okay, so it's basically just another matching method from nearest neighbor or within a caliper. So they use a caliper here, and the caliper basically determines You can think about it as a caliper instrument. It's just determining how close or how far, how granular you want your matches to be. And so we can set that, and that's going to give us different results each time we put a different PS match. So if we do PS match 2, treated, P score is score again, outcome is earnings 78, and caliper, let's say it's really small, right? We want it to be very, very close, our matches. So now this idea of common support shows here. So for your untreated units, you have 2,490 on support. You have 271 on support for the treated. You have 0 off support and 26 that are off support. So your average treatment untreated is 6,067, which is still really large here compared to whether compared to what the treatment effects were before. So let's try to make the caliper even smaller. What if it's 0.001? Okay, so now your average treatment on treatment for the unmatched is this, but for your matched is 6,412. Let's see what if the caliper is bigger. So now we have common support. So now we have a smaller average treated on treatment. And it basically stops there. Now it's not changing at all. So let's just kind of see if we can get more information or a better description of what the caliper does. So all of this has a good one, so let's do help PS match 2. So matching methods to adjust for pre-treatment observable differences between a group of treated and untreated. Okay. So these are the different matching techniques that one can do. We can trim common support by dropping a percent of treatment observations. The caliper is a value for maximum distance of controls, used to perform nearest neighbors within caliper, radius matching, and I can't say this. This one-to-one matching. So basically, it's determining how close you want your nearest neighbor, the radius, to be. So you can think about drawing like a circle. So the smaller it is, when it was 0.1, 0.001, means that the stricter that we're being, the larger it is, the less strict we're being on the matches. So we can see that the average treatment effect on the treated actually is bigger when we're matching better, and that's what we found before. When our matches are really close, that means we actually find a very high treatment effect, because we're observing just the differences on treatment, basically training, rather than the differences in, age or schools of education and such. So now after running this command, we can run the PS test command. We can read more about what that is. So it's a covariate imbalance testing and graphing. So it's actually going to help us visualize what our covariates look like, the balance of it. So PS test, age, black. So these are the covariates that we want it to show us on the graph. The ones that we're listing. We tell it to graph at the end. School not found. Maybe it's still education. Let's try that. So I really like this graph because it tells us the standardized percent of bias across covariates, so we can see upward and downward bias. So our black and maybe Hispanic are pretty balanced between treatment and control, but other than that, our age is negatively biased. earnings positive, no degree, education, married, all positive in comparison to the treated and the non-treated sample for covariates when we're using this matching technique. So I shouldn't say treated and non-treated, I should say treated and matched sample. So our covariants are still not balanced even after we do all of these matching exercises. And let me just rerun this so that it's 0.01. And we get something a little bit better. So remember I had changed it to 0.9. And now we see that, okay, on the demographic black, it's very balanced. There's no bias. Earnings is a lot less bias, like maybe about 3%. And Hispanic about 4%. No degrees about 5%. But you still got education and married having a high percentage of bias across covariates and age having a negative bias. So we can still tell after all of this effort that we put for matching, we still have a percentage of bias across the covariates, but at least they're similar, closer to the same as the experimental treated group. And so I'm going to leave you guys off here. I know we've covered a lot today, but I wanted to show you guys kind of what Scott Cunningham does in the book so that that stuff makes sense and you guys can recreate it if you'd like, as well as an easier way to run this matching for your homework or for your own research. But it's definitely one of those techniques you want to, read thoroughly on and make sure that you understand how to interpret the results as well as the code, and also understanding when it's appropriate to use and when it is not appropriate to use, and whether your results still hold and are strong. Understanding that the CIA assumption is met, and Scott makes a very good point that you really need your DAG, your directed acyclical graph, to tell whether you've satisfied backdoor criterion, satisfied your CIA. And so definitely in your own research, it's a helpful tool to draw that DAG to see whether you can satisfy your CIA criterion and then use this method. But yeah, guys, thanks for following along, and definitely reach out to me if you have any questions or concerns in this. Again, please write down any questions or concerns while you're going through it. Obviously, try your best to go over it a few times, see if it makes sense, but if it's just not making sense, the TA session's a good time to bring this up and we can all go over it together. Okay, guys, thanks and good luck.